Welcome to ELET B70 Mechanical Systems. This is your professor, Roy Allard. This lecture is on fasteners. This is based on Chapter 2 of the textbook. These are the topics for this presentation. Our common threaded fasteners today are based on Archimedes' principle of the screw. You can see the screw he designed to lift water from a lower part up to an upper part. It came out of a river and he was able to lift it for irrigation. And this was done in about 250 BC. Here's a common threaded fastener. This would actually be a nut and a bolt. And here's Archimedes' screw. You can see how it would elevate the water out of the river by turning the handle and then put it in another area. Over the years, the screw has evolved into what we see today. So when do we call it a screw? When do we call it a bolt? There's really no universally accepted distinction between a screw and a bolt. The Machinery Handbook described the distinction as follows. So a bolt is externally threaded. Well, a screw is externally threaded as well. It's designed for insertion through holes in assembled parts. Normally is tightened by releasing or torquing a nut. So here's a key distinction. There's a nut that goes with the bolt. An externally threaded fastener which is prevented from being turned during assembly and which can be tightened or released only by torquing a nut is also a bolt. So example would be a carriage bolt or a round head bolt, track bolt. So the bolt has something underneath the head that is inset, like on a carriage bolt for a gate hinge, for example. The hole that the bolt goes through in the gate hinge is actually square. And there's a protrusion on the underneath side of the bolt head which goes in that square. So it's holding it from being turned, and then we torque the nut on the back side. Kind of a version of a security bolt. The handbook says a screw is externally threaded, same as a bolt, capable of being inserted into holes in assembled parts. Now here's a little bit different of mating with a preformed internal thread. So that would be a bolt going into a machined piece of metal with threads in it, or forming its own thread. This distinguishes the difference between a screw and a bolt. A bolt does not have those cutting edges to form its own thread, where a screw going through wood or in some types of plastic can actually make its own thread, and it's tightened or released by torquing the head of the screw. An externally threaded fastener that has thread from form which prohibits assembly with a nut having a straight thread and has multiple pitch length is a screw. So wood screws, tapping screws. So a nut would not go on a screw is what that is saying. So you're really not going to be wrong if you call a screw a bolt or a bolt a screw. But try to use the name. It'll probably help in industry to find out what your company calls them and probably stick with that. But this should give you a really good basis of the difference between a screw and a bolt. This diagram will also help. These are some standard screw and bolt types. So if we looked at these, and this we actually call a machine screw. It has a button head on it, but we call these machine screws. But it's actually fitted for a nut to go on. So ultimately, this would be a bolt. But we're really looking at the different types of heads here. So this is a socket shoulder. You can see there's no threads up here. This is a button head. It's noticed or identified by being very flat and thin and wider, like the button that's going to go through a buttonhole in a shirt. Here's a hex head. This is our standard bolt. And then here's this round head machine screw, similar to the button head. So this is more round. It's almost like a half circle, and it's flat underneath, and it has threads for a nut to go on. But look at right here, we call it a machine screw. And in a hardware store, it will be called a machine screw. Here's a flat head screw, so the top of it is flat, and it has an angle that sets into the material, so the head fits flush with the top surface of the material. This is a set screw. We'll be going more into set screws. So it would go in to lock an object to a shaft. Then here's our socket head. So this is our Allen head, our six-sided, kind of a reverse hex head in a way. And then we have a book screw. If you're on a construction site where they have big building plans, a lot of times the plans are held together with these book screws. Here is a lag screw. Now, lag screw makes sense because a nut cannot go on this. But a book screw, well, certainly this is the nut. It's just not in the normal shape of a nut. Here's our carriage bolt. So here is the square form underneath. And there's nothing on the top. That's just a solid piece of metal. There's no groove or any space for a fastener to insert in the top of a carriage bolt. And whatever we're putting this bolt in, it would inset into a square opening, which keeps it from turning, and then we can just tighten and loosen by torquing the nut on the back side. And here is a sheet metal screw. So really, if we're talking about screws, we're looking at this screw and this screw. Everything else is considered a bolt because a nut can go on it. Now let's talk about some of the screw thread nomenclature. So I really like these two diagrams, and both of them have their advantages and disadvantages. So let's look at the crest, the point of the thread. So this is the crest right here, the largest point of the thread. We can also see it very clearly in this diagram. Each one of these is called a crest. The root is the inside edge of the thread, or the valley below the crest. So we see it here, and we also see it on this diagram up here. The thread angle, most standard threads have a 60-degree thread angle. So that is this angle right here between the facing crests, or the sides going down into the root. That is the thread angle. The helix angle is where the threads are arranged in a helical curve, in a helix, and the angle is measured between the facing crests. So there's a slight difference from 90 degrees up from this point to this point. And that's the angle of the thread. You can kind of see it here. You can see all these are at angles. And that's the helix angle as it's twisting around the diameter of the thread or the screw or the bolt. Next we have the major diameter. This is a distance from one crest to the other side of the crest. This determines the nominal size. What hole will this screw or bolt go in? I went back a slide because you can see we have the major diameter across the threads from crest on one side to crest on the other side. So if this was considered to be a 1/2 inch bolt, the major diameter would be a 1/2 inch, and this bolt, the threads would go through a 1/2 inch hole. Now the next thing is the minor diameter. So the minor diameter is from the root to the root. So this is the minor diameter in here. Then we have the pitch diameter. The pitch diameter is halfway between the crest and the root on one side, and the same thing on the other side. That's considered the pitch diameter. Now these diameters, major, minor, and root, are pretty important. For instance, if we were to drill a hole for a screw and we drilled it in the major diameter, then the screw wouldn't have anything to bite into because it would be from the edge of one crest to the other, and the screw would just slip into the hole. Now, if we went and drilled it smaller than the minor diameter, then not only do the threads have to fit through the opening, but part of the shank of the screw itself. And that would make it very difficult, and most likely whatever we're inserting it into, whatever the material is, it's probably going to break or crack. So these diameters are very important. Here's another diagram that shows a similar measurements, but it really only shows it cutting the screw or the thread down to where the shank is. These are just the threads cut into it. The root is right here and the crests are on the top. So this is sometimes a hard concept to follow because it's just showing the threads and not the metal shank that's in between. If you're really into graphics, then this is probably an easy diagram or illustration to make use of. This slide shows the previous diagram enlarged. So again, the crest is the tip of the thread, the cutting edge, and the root is the valley of that thread. The thread angle are between facing valley and crest, the opening, and then the pitch is going to be between one thread angle and the other from side to side. It's very hard to illustrate that on here. And you can see the major, the root, and the minor diameters. So here you can see the thread angle between these faces, and you can also see the helix angle because it's going at an angle. So thread pitch is a distance between the two crests. So from one crest to another. The common way to express thread pitch is by specifying the number of threads per inch. Just like we talked about on the previous lecture for hacksaw teeth on a blade, there's so many teeth per inch. Well, this is the same thing, only we're talking about threads instead of teeth. And we could kind of consider these teeth, especially in a screw, because they do bite into the material. A bolt, however, doesn't bite into the material. A threaded nut goes on. So we just look at how many threads are in each inch of length of the screw or bolt, and that gives us the threads per inch. So we can measure them using a screw thread or thread pitch gauge. So this actually measures the major diameter, and then we take one of these screw thread gauges and they will fit completely in the valleys, into the root, across the crest. And once we find the one that fits the best, then we know what TPI our threads are. And this can be very handy when we're doing tap and die work, when we're cutting new threads, and we need to see what pitch the bolt is or nut. We can use the thread pitch gauge to do that. There are different types of threads. Unified National Coarse and Unified National Fine threads are what we use here in the US and mostly all over. There is the British standard Whiteworth. And Sir Whiteworth actually created the screw thread, and it was the first standardized thread. But it's mainly used for British pipe threads. So you can see here is a 3/4 inch, so its major diameter is 3/4 inch, and it's Unified National Fine right here, UNF. And then here is a coarse thread right here. So the difference between a fine thread and a coarse thread is actually the distance between the crests. You can see that. These three on the bottom are coarse, and these two on the top are fine. This just happens to be a metric fine thread as opposed to a unified national fine thread. So believe it or not, everything in industry is tied to some standard. So we have different fastener standards. We have ANSI and ASME, American National Standards Institute, and the American Society for Testing of Materials. Of course, in the automotive arena, we have Society of Automotive Engineers, and then International Organizations for Standards, which covers international standards. Now let's talk about the difference of coarse and fine threads. So the advantages of coarse threads are that they're more economical than fine threads. There's less threads, so they're easier to manufacture, so they cost less. They assemble and disassemble more quickly and easily. There are fewer threads per inch, so when we're turning it, each turn moves farther into our work area. They tolerate more contamination and abuse because there's a lot bigger difference between the major and the minor diameters, so there's a lot more space to be able to have abuse of grime and dirt. They tolerate corrosive attack with less strength loss because there's more meat, the material of the crests. They have a less tendency, or a lower tendency, to cross thread because there's fewer threads, so the nut goes on more easily. And they have better fatigue resistance. But let's look now at fine threads. They have more holding power because of the greater surface area the threads have in contact with each other. So for example, if we have a machine screw which has 32 threads per inch, that would be a fine thread, a 1032, 10 is the size, versus a coarse thread, 1024, for each inch that the screw goes in, we have many more threads. There's actually 8 more threads in that inch from 24 to 32. So it has more holding power and more contact. They have more shear strength because of a smaller thread depth. They're easier to tap because we're removing less material with the cutters of the taps and the dies. They work better for thin materials because there's more threads per inch. If we only have a very thin surface to grab onto, a fine thread may only put one thread in contact with the material. With a coarse thread, a coarse thread may only put one thread in contact with the material. Whereas a fine thread may put many threads, 3 or 4 or 5, in contact with the material. They also are better for fine adjustments because more turns are required to provide the same amount of movement than a coarse thread. So we can look at the coarse thread advantages, and those actually are disadvantages of the fine threads, and vice versa. Now let's take a look at the parts of a bolt. So here we have the bolt head, And the head can be in a lot of different configurations. This happens to be a hex head bolt. Then we have the radius on the shank. So this is the shank, and we call the distance of the shank from the threads to the head the grip length. Now the nominal length is the entire portion from just under the head. We don't count from the top of the head, but under, and this is the nominal length to the end. Run out is the taper from the root of the last thread up onto the shank. And then you can see we have the threads. We learned all about the thread nomenclature, the crests, the roots, major, minor diameters, what have you. Here's a table of the national, unified national threads. So these are the American threads, not the metric. And you could see where I talked about the number 10 machine screw having 24 threads per inch for coarse and 32 for fine. So once we drop below 1/4 of an inch, we go into numbers. The larger the number, the larger the diameter. The smaller the number, the smaller the diameter. And you can see the different decimal equivalent diameters. Of course, 1/4 inch is 0.25 decimal. And we have the normal 1/4 20. And so generally we'll call it 1/4 20. 1/4 inch, 20 threads per inch. And then the fine thread version of 1/4 inch is 1/4 28. So you can see if we have a 1/4 inch bolt, that is the major diameter, and we actually have a 3/8 inch head on the top of that. So we would use a 3/8 inch wrench, and sometimes we would use a 7/16 inch. It depends on the manufacturer of this fastener. But a 3/8 inch wrench for a 1/4 inch bolt. That's what this is saying. And you can also see that we have the root diameter. So you can see between fine and coarse, look at this is 8 threads. 8 threads here. 8 threads here. But as we start to get larger, we get fewer. Here's only 11 thread difference. Here's 6 thread difference. So we try to keep quite a few threads difference, and you'll definitely be able to tell by looking at it side by side from a coarse to a fine. And once you get used and experience to using fasteners, you can quickly look at them based on the diameter, and you can tell that this is a 1/2 inch, 13 threads, or 20. There's 7 more threads on a fine thread 1/2 inch bolt, and you'll be able to tell that by looking at it as you get used to using these nuts and bolts and different fasteners. Next, we're talking about class of fit. So screw threads are divided into classes, and it's determined by their tolerance and allowances. So let's define what tolerance and allowance means. Tolerance is the amount of size differences allowed from the exact size. Allowances are how loosely or tightly they fit with their mating parts. American standard screw threads have 3 classes and then have a letter after the class. Let's look at the 3 classes. Class 1 has a large allowance for a loose fit, so very few fasteners are made with this class because they just don't have the strength because of the loose fitting allowance. Class 2 are between loose and tight, and they're the most common in the United States. Class 3 have a tight fit, and they're used in critical applications such as aerospace. They're harder to make because the tolerance is so much tighter. So we have to have a lot higher quality control to make a Class 3 fastener than a Class 2. Now the letters after, we have A or B. A means that it has an external thread, where B would be an internal thread. So Class 2A would be a bolt thread, and class 2B would be the accompanying nut thread. The International Standards Organization have threads with a designated fit. They're a combination of letters and numbers. For example, the HG/7H. In this course, we're not going to worry about the fit designations of the metric screw threads, so you won't be tested on this. This slide talks about bolt grades. And grades refer to the strength of the actual material. So for Unified in the US, we actually have marks on them. So you can see this has 3 marks, this has many more than 3, actually 6 marks, and so on. So if there are no marks, we have grade 1 or grade 2. They won't have any marks. 3 marks will be a grade 5 bolt. 6 marks is a grade 8 bolt. So the higher the grade number, the higher the strength, because grade refers to the strength, the material. So for grades 5 and 8 being stronger than grades 1 and 2, they're also able to be heat treated. So let's say, for example, you have a machine at work, and every so often, maybe about every 6 weeks, you have a bolt that breaks. So if you have been maintaining this machine from brand new, you definitely need to look at the root cause of why the bolt keeps breaking. Now, if you haven't maintained this machine from brand new, how do you know that the bolt that you have removed that is broken is actually the correct bolt to be in that machine? Here's where you make yourself valuable to your employee. And it's very important because valued employees will be there much longer and will be always employed by the company they're at. So what we'd want to do is maybe look at the machine manual. What is the specified part for that bolt to go in that machine? Maybe what happened, it might have been a grade 8, like this bottom one down here. And for some reason, the machine got taken apart, the bolt got lost, and so someone went and grabbed another bolt. And they might have grabbed a grade 5, not remembering that they removed a grade 8. Well, a grade 5 is not as strong as a grade 8 bolt. So now, under fatigue of the operating of the machine, that bolt continues to break every 6 weeks or so, depending on how much the machine is used. So by you examining and putting the correct grade 8 bolt in there, no longer does that bolt break, and the machine has more uptime. It's more productive, and more material is output. You've just saved your company a lot of money in operations costs, and that makes you valuable to the company. One of your greatest resources is the telephone. Call the manufacturer when you're having a problem like breaking bolts. Talk to them about it. See what they recommend. Make sure you're putting the correct bolt back in that machine. It's very important. When looking at metric bolts, the strength are designated by numbers. The number provides some information on the strength. Again, we're not going to get into the metric strength or the classes. Nuts also have strengths, just like the bolts are marked. So you can see the bolts are marked here. These are the bolt heads. And the nuts have lines in them. So for grade 2, after June 1979, we have no mark on our nut. Grade 6 has 2 marks, 120 degrees apart. And then grade 8 has 2 marks, but they're right next to each other on the facing sides of the hex head. Then we change from the two marks to a mark and a dot. But still, they're right next to each other versus further apart on every other face. So in your homework this week, the knowledge base, you'll be identifying bolt thread strength and nut strength. One of the first couple of slides, we actually looked at the different types of heads, but this slide gives you a much better picture of those heads. So you can see these are flat heads, which are flat with the surface of the material, or might even be inset. So they have an angle on the underneath, and that would set in and then grab the material. This is a pan head, so it's kind of like a round head that's flattened on top. Here's our round head. This would be like a half circle. Remember the shoulder bolt? So this will go through something, and then a nut can be put on it. And depending on the width of material it goes through, whatever we're fastening may be able to hinge or move. And it depends on what the shoulder bolt is being used for. Now here's a carriage bolt, a little bigger picture, and it's square on the underneath. This is what's going to set into the material so it won't turn. And then we thread a nut on the back side. Here's an oval head. So you can see the difference between the flat, the pan, and the round, and it's kind of more of an oval shape underneath and on top. Here's our standard hex head. And here's our socket head, where we would use an Allen wrench to go in there and turn it, to tighten it and loosen. In automotive and big machines, we see a lot of flange heads. So it's like a hex head with a built-in washer to it. And it's all one piece, it's all part of the actual bolt. But this is the head, flange head. And then the button head, which is flatter and wider than most of the other heads. They're commonly used for furniture assembly. So when you're identifying heads in the knowledge base, be sure to look at the instructions. It clearly states to just insert the type of the head and do not include the word head. So if you've identified a round head, what are you going to put in? You're not going to type in round head. You're going to type in round. If it's a flat head, you'll type in the word flat, and that is all. So make sure you pay attention to the instructions on the knowledge bases. These are industrial threaded fastener types, and these are to hold objects onto shafts. So this spline here would go on a shaft, and we tighten down this set screw. Plain cut points are found on bolts and machine screws, and they're not meant to be used for in-holding force. So this would be plain here. Where when we have a cone point on a set screw, and there's many different types of points, they're used to lock an object to the shaft, a set screw. And they're a headless fastener. So we actually use an Allen wrench normally that is cut inside of this to tighten it and loosen it. So then it sinks into the material and doesn't protrude out over the material. This cone point has the most holding force, but they're used for more permanent installations because they cause the most damage to the shaft. This cone point will be very hard in relation to the shaft, and it can dig in there and actually dent and cut into the shaft. Some other points are the oval point. So this will have the least holding power. It's not going to hold very much. And then we have the flat point. They're better than the oval point, but still not as good as the cone point. They're mainly used where there's a flattened shaft, and it can go through whatever's being placed on this shaft and then press against this flattened part so it won't spin and twist off. The dog point resemble a dowel on the end, and they actually go into a slot that is machined or drilled in the shaft. So they will go in quite a ways into the shaft itself. And this is most often used for permanent mounting, similar to the cone point. Next we have the knurled point set screw. So it's got kind of some biting force on the underneath. It's knurling. And this is an example of knurling. We actually have a knurling tool in the machine shop next door. If any of you have taken machining, maybe you've done some knurling. I remember when my son was working in a machine shop, he made some custom potentiometer knobs for guitars, for homemade guitars. And he actually knurled them himself with the knurling machine in the machine shop. So when we turn them counterclockwise, the knurls are used to resist vibration and prevent this fastener from loosening or coming out. It leaves a little burr on the shaft like a cone point, but not near as much damage as a cone point would leave. This is really the most common of industrial set screws that you'll find out in industry, and it's also designed for permanent installation. So we talked a lot about threads, but how would we make them if we wanted to cut our own threads through material or to repair the threads of a nut? Well, we would use a tap. A tap is used to make internal threads like on a nut, and a die is used to make external threads like on a bolt. So on the taps there are three types. You can see we have the taper, the plug, and the bottom. So the bottom has no taper at all, and it will make threads clear to the bottom. It's a little harder to stop because it cuts when we first insert it. The plug tap has a small amount of taper, and the taper tap has a large amount of taper. So you can see when we're screwing this into material or a nut to recut the thread, you can see we have to put it in quite a ways. But it makes it very easy to start cutting the threads, and then they cut fully in this range. Dies have 4 or 5 cutting ribs tapered, so they're easier to start. It'll actually say on the die, start from this side, and so that's the side you would screw on to the bolt first, because it has that taper. In lab, I'll show you some different taps and some different dies. They come in all sizes for all size of fasteners, from the smallest machine screw to the largest bolt. So we would use a tap, for example, when we're making a part of a machine or a bracket and we want to be able to screw a bolt in it, thread a fastener into the hole. So a lot of times when we're machining this piece of metal, we'll actually have the machine cut the threads. But if we're going to do it, or we buy a piece of metal that we need to cut threads into, we would use a chart, and it would usually come with the tap and die set. And it would have the drill bit size to use for the proper thread diameter. So we would follow, and sometimes it's on the tap itself printed on the side, but most of the time it's the size and the threads, like 1/4 20 would be coarse, or 1/4 28 for a fine thread tap. So what we would do, we'd go to the chart. Sometimes it's on the inside cover of the case that holds these, and sometimes it's just a loose card. So we'd look at that and we'd choose the proper size drill bit. We would drill through the material with the drill bit as straight as possible, and then we'd take our tap, and we would have to use a taper tap because it would be very hard to start a bottom tap in this situation. And the taper tap will start to screw in. You'll actually screw this in by hand, making sure it's straight up and down and perpendicular to the material. And then we'd take our tap wrench and we'd start to turn it through the material. It's very important that we use the proper drill bit size to bore the hole in the material that matches the tap size that we're going to use, or else it will be very difficult to cut the threads if the hole is not big enough, or we won't cut the threads deep enough if the hole we drill is too big. So don't just eye it, look at the chart and make sure you use the proper hole size. Another way to repair threads, as opposed to using a tap, is using a thread insert. So when the inside threads are damaged, we can use an appropriate thread insert. We call them helicoils because that's a manufacturer. It's actually a threaded insert. It comes with a bit, it comes with a number of different threaded inserts and a tool to insert them. So once we put these in there and we start to screw the bolt, they tighten up and make this material almost like it was one piece of material. They've been used a lot in the automotive industry, especially when maybe you put in a spark plug and you cross-threaded it. So instead of taking off the whole cylinder head and having it fixed or machined or replaced, they make helicoils that will thread in the thread insert, so then you can put a spark plug back in the hole. So these can be used in industry, around the house, anywhere you need to create a thread. There's also some thread inserts that you can put inside wood, and they have an actual wood screw thread on the outside and a machine screw or a bolt thread on the inside. And they have a way that you use a flat blade screwdriver to install it. So you might want to do that where you want to make threads in a piece of wood where you're going to assemble and disassemble a cover on this piece of wood often. Because when you do that with a wood screw, eventually the wood screw is going to strip the hole in the wood, especially if it's a softer wood or you're removing and replacing that screw often. So thread inserts can be used in metal and in wood. That concludes this lecture on fasteners. I hope you've enjoyed it and can take some of the information you've learned to the job site with you. Remember, you want to be of value to your employee. So use your knowledge and your education to make sure that you are. If you have any questions after watching this video and reading the textbook, please post them in the Q&A discussion. Thank you very much for watching.